So before we get started on today's stuff, I want to go back and review quickly some of the stuff that we talked about on Friday, which was naming organic molecules, particularly alkanes is what we've been focusing on. And there are three parts to every name, and what are those three parts? We have a prefix, we have a parent, and we have a suffix, right? For the purposes of an alkane, the suffix is going to be what? A-N-E, ane, right? So we're talking about alkanes, right? The parent tells us what? How many carbons? In the longest continuous chain, right? It's kind of important to have those words in there. And the prefix is where things get complicated, right? What does the prefix tell us? It'll tell us how many substituents we have, but it'll also tell us what? Where they are and what they are, right? So we're going to have a lot of information in that prefix. And so here I've got an example on the board. So even though we're go prefix, parent, suffix, what's the first thing that we do? Yeah, we find the parent, right? That's the first thing that we're going to do. And it has to be the continuous chain. So we can go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. Looks like 8 is going to be the longest chain, right? So what do we do once we've identified the longest chain? Pardon? Well, we're going to do that next, but what's the first thing I told you all to do? Circle it, right? Circle the longest parent chain. Put it in a circle of some sort. Everything that exists within that circle is the parent and will not find its way in the prefix at all, because those carbons are taken care of by the parent. So what's the parent? It's oct is the parent. The suffix is ane, so it's going to be an octane derivative, right? So it's some sort of octane derivative. How many substituents do I have? I've got 4 substituents. I've got one here, I've got one here, I've got one here, and I've got one here. Right? What are they? Okay, these 3 are methyls, and then this is an ethyl. So I've got some type of methyl, or trimethyl actually, ethyl octane. Now, I have to figure out where everything's located, right? And I can either number from the left to the right or the right to the left. Which one would be correct in this case? The left to the right. 1, 2, 3, 4, 5, 6, 7, 8. And why is that correct and not the other way? All right, the first point of branching for the substituents, right? Going from left to right. And there's no way going the other way that I would have an equal number, so I don't have to worry about all those other little caveats in those rules, right? So left to right is the right numbering system. So let's name it. So what's going to be the first substituent that gets named? It's ethyl. It's 5. Do I just write 5-ethyl? What do I write? 5-ethyl. Pardon? Why is it first? Yeah, E comes before M in the alphabet, right? So we're going to alphabetize them. So we have 5-ethyl, then what? 2, 3, 4. You're almost there. 2, 3, 4. 2, 3, 4 what? Trimethyl octane. Right? That tells us everything. Notice that numbers and letters are separated by hyphens, and numbers are separated by commas. Right? So this tells us very systematically how to assemble this molecule. Right? I'm going to have an ethyl group on carbon number 5. On carbons 2, 3, and 4, I'm going to have methyl groups, and it's going to be on an octane parent. I can type that into a computer program, and it can spit out the structure for me. Okay, so it's that kind of language that we're working with here. So today we're going to continue talking about some naming. Okay, we're going to start talking about cycloalkanes, things that make rings. Okay. So how do we name them? How do we count the number of rings? Okay. How do we find out how many rings are actually in a cyclic molecule? How do we name these cyclic molecules? And again, don't forget, you all aren't going to be experts at this naming stuff for a while. It's okay. You're going to have to work some problems and get through it. Okay? We could spend a whole 2 weeks on just naming alkanes and practicing, but we just don't have enough time to devote to all that. Okay? So we're going to talk about some cyclic alkanes, or cycloalkanes as we prefer to call them. We're going to talk about rotation around sigma bonds. We're going to see how we can have free rotation around the bond and why that's important. We're going to talk about a projection called a Newman projection. In other words, how do we represent something as it rotates around a sigma bond? We use what's known as a Newman projection to do that. And we're really not going to get too much into conformational analysis today, but I'm going to talk to you a little bit about the fact that rotation around a sigma bond gives different energies to the molecule. And so even though we say something has free rotation, it doesn't mean that it's going to exist in all possible what we call conformers all the time. Okay? So cycloalkanes, the nomenclature is very, very similar to the nomenclature of a normal alkane, except we're going to put cyclo in the name. Okay? So you're going to have your prefix. It's going to tell you where the substituents are, what they are, right? It's going to tell you how many. You're going to have the word cyclo right before the word, the parent name, and then you're going to have the suffix. And the suffix, again, since we're dealing with cycloalkanes, is going to be A and E. So really, the trick is just to remember to add the word cyclo. Okay? So if we look at this molecule, okay, the first thing that you're going to have to do is find the parent. And the parent is a 6-membered ring. So it would be cyclohexane, right? What are the substituents? I've got an ethyl group and I have a methyl group. Very good. Okay? And so you're going to name and number the substituents. No number is needed to indicate the location of a single substituent. For example, here I have a methyl group on cyclohexane. It's just methyl cyclohexane. You don't say 1-methyl cyclohexane. Is it incorrect to say 1-methyl cyclohexane? No, but it's irrelevant. Because no matter where you put that methyl group, it will always be carbon number 1. So it doesn't matter when you have one substituent. And so we drop it. Here we have a cyclopentane ring, and attached to it is what's called a tert-butyl group. Where do we get the term tert-butyl? Okay, yes, it is on a, if you looked at the butane part, right, where if this had the hydrogen still on it, it would have been a tertiary carbon. It's no longer a tertiary carbon because it's bound to a cyclopentane ring, but yes, the hydrogen that you removed to get the alkyl group would have been a tertiary carbon. I like to remember it because it looks like a T, and we frequently call it T-butyl instead of tert-butyl, okay? So there we have tert-butyl cyclopentane, and notice there's no number. If the ring has more than one substituent, numbers start to become important, okay? And so if you look at our, well, this isn't exactly the previous example. This is a dimethyl cyclohexane. You can number either in a clockwise fashion, or we can number in a counterclockwise fashion. And what did we want to do on Friday for all of our substituents? We always wanted them to have the lowest possible location number, right? The same thing is going to happen here. And so you start at one of the substituents and you number such that you get the lowest possible numbering. And that would be clockwise, starting here with 1, 2, 3. Going in a counterclockwise, you would have a 1, 5. Lower numbers are 1, 3. 1, 5 is too high. So that would be the incorrect numbering system. The one on the left is correct. And so we have 1,3-dimethyl cyclohexane. Very similar to how you would name a regular alkane, except now we just have the cyclo in front of the parent name. Okay? With two different substituents, you're going to number the ring to assign the lowest number to the substituents in an alphabetical fashion. Okay, so here we have cyclohexane again, so it's going to be cyclohexane as the parent. We've got an ethyl group and a methyl group, and we could start numbering 1, 2, 3, but we could also do 1, 2, 3 and still have the same numbers for both of them, right? 1 and 3, no matter which way you do it. but you always are going to assign number 1 to the substituent based on where it comes in the alphabet. So ethyl comes before methyl, and so you're going to start here and number clockwise. So we have 1 ethyl, 3 methyl, cyclohexane is the name of that particular molecule. Okay? Now, you can have a situation where you have long chains and you have to decide what's the parent. It depends on which is longest. Okay? If you look at the example on the left, you'll notice we have 6 carbons in the ring, 4 carbons in the chain. 6 is greater than 4, so 6 becomes the parent. So it's going to be a cyclohexane molecule. And so this is a butyl group, and so we would say butyl cyclohexane. However, the one on the right, you can clearly see the chain is longer than the ring. And so we're going to name this as the normal alkane or N-alkane with a cyclobutyl substituent on it. So this becomes our parent. This is what we would circle. This becomes the substituent at carbon number 1. Okay, so it is 1-cyclobutyl hexane. Because you took cyclobutane, you removed a hydrogen, and you had the alkyl group. Okay? So you're going to have to count the chain when you have these long chains attached to these ring compounds. Okay? If the chain is longer than the ring, we're going to name it as the chain with a ring substituent. If it's the other way around, it's going to be a cycloalkane parent with a chain alkyl group attached to it. Okay? There are also some common names that you need to be familiar with. These are not derived based on anything rationally other than how they look. Okay? And they've stuck, and IUPAC has adopted them. Okay? So for example, looks like a cube. It's known as cubane. Makes sense, right? What's kind of weird about cubane if you look at it? What's the hybridization of the carbons? They are sp3 hybridized, right? What's the bond angles in an sp3 hybridized carbon atom? Tetrahedral, 109.5. What are they in a cube? 90 degrees. This is a very unusual molecule. Okay? It has a lot of what we call ring strain. We'll learn more about that later. It can be made. It's actually stable to a degree. And it's also been explored quite a lot by the Navy and other people in the past. I don't think they're looking at it too much anymore as a potential explosive, putting other substituents on it. So cubane has received a lot of attention in the past. Housane looks like a house, right? Kind of looks like a house. Churchane kind of looks like a steeple right on top of a house. And then, of course, basketane. Looks like you've got a little handle, carry a basket of eggs with you, right? These are common names, and there are more common names than just these, but these are the ones that I want you to kind of remember, okay? So these are the ones that we really don't have a great way to name them systematically, and the common name that people started using just kind of stuck, and so that's where we're at. So you have cubane, housane, churchane, basketane. Now, you can have cyclic molecules that have more than one ring. Okay, so for example, the molecule that we look at there. How many rings are there, do you think? Just by looking at it, how many rings do you think that molecule has? How many? You said 3? Okay. And that makes some sense. Let's build the model. I've got enough parts out here to build this model real quick, so I'm going to build a cyclohexane ring. You can build along if you've got parts put together. So there's 6 carbons. I'm going to connect them together in a ring. And then we've got 1 additional carbon in that Pepto-Bismol kind of color, right? So there we are. That's that molecule right there. And you can see the projection. See how those look pretty much so the same, right? Other than the fact that the hydrogens are actually shown instead of just being abbreviated. And so I think Anna was saying, if we start like maybe right here and we go around, there's a ring, right? Because I'm never lifting my finger, right? So that's a ring, and a ring is kind of starting at a point and being able to get back there without lifting your finger. Here looks like a ring, right? And this looks like a ring, right? It kind of looks like there should be 3 rings. However, that's incorrect. There are only 2 rings. This is a bicyclic molecule. And the reason that I know there are 2 rings is because I can pull it apart twice and get everything to be open. So it's how many times you have to disconnect a bond to get the ring completely open and being non-cyclic, or acyclic as we like to say. Okay? So it's not just how many times I can trace around a ring, it's how many disconnections lead to that ring. Okay? And so this is what we call a bicyclic compound. And there's ways to name these. Okay? And if you look at it, you'll notice that we have a 2-carbon bridge. We have another 2-carbon bridge. And we have a 1-carbon bridge. These 2 carbons at the ends that are here in red are called the bridge head carbons. They connect the rings together. Okay? So we have the bridge heads. We have a 2-carbon bridge, we have a 2-carbon bridge, and we have a 1-carbon bridge. And so the way that I like to think of this, imagine that you're standing on this side of the river and you want to get on this side of the river. You can take a 1-carbon bridge to get there, you can take a 2-carbon bridge to get to where you want to be, or another 2-carbon bridge. Okay? So the stuff in between, I can't go straight from here to here because there's no bond, right? So that's how I identify the bridge heads. And the bridge heads are the things that connect those bridges together. Okay? So you need to be able to identify the bridges and the bridge heads, which isn't too difficult to do. Okay? That's how we would draw it on a flat piece of paper. Okay? And now how do we name it? Well, we notice that we have 7 carbons in the bicyclic molecule. So what's the parent? If we have 7 carbons, what's going to be the parent? It's going to be heptane. It's going to be a heptane parent, right? So we have 2 rings, so we're going to call it bicycloheptane. And there's a big space here for a reason. Can anybody tell me what needs to go in that space? What needs to go in that space are the numbers for the bridges. Okay, we have to identify those. Okay? So we've got 2 2-carbon bridges and a single 1-carbon bridge. So this becomes bicyclo 2.2.1 heptane. Notice we are not separating the numbers in this case with a comma, but rather by a period. So bicycloheptane tells me that I've got 7 carbons making a bicyclic structure. The numbers in there tell me that I have a 2-carbon bridge, a 2-carbon bridge, and a 1-carbon bridge. We go in descending order. Most carbons, next most carbons, least number of carbons. Okay? So now if you've got the model built, let's build something a little different. And let's take the same number of carbons, 7, and let's put it maybe over here. That's kind of a strange looking little molecule, right? So it's still bicycloheptane, but what would I put in the brackets now? Here's my bridge heads. I've got a 3-carbon bridge, and I've got 2 1-carbon bridges, right? So this would be bicyclo 3, 1, 1 heptane. Okay? Let's go back to one that makes a little more sense. The other one would be highly strained. But nonetheless, you get the idea, right? We can have those types of rings. What if we had something that looked like this? How would we name that? Octane. Yep, because I've got 8 total carbons, right? So it's going to be an octane parent. And I've got a 2-carbon bridge, a 2-carbon bridge, and a 2-carbon bridge. These are my bridge heads. So it's 2.2.2 octane. Okay. So how do we identify the number of rings in a bicyclic or in a cyclic compound? Number of disconnections. Now, on an exam, I might give you a molecule that has a lot of rings, maybe even more rings than you have pieces to build your model kit with. So how would you do it then? The way that I do it is I actually draw it out with a pencil, and I'd take my eraser and I start erasing bonds, and I just count how many erasures I have to get before I have the molecule in completely the acyclic form. Okay, that's the easiest way to do it. With your model kit, you can build a model maybe up to 4 rings, depending on the size. Okay? But beyond that, you're really going to have to depend on pencil and paper. Okay? So let's build some models. So what I want you to do is get your model kit out, and I want you to build an alkene. We're going to start with that. So you need 2 of these gray pieces that are labeled sp2, and you need one of these pi bond pieces. And you just snap them together. Okay? So you should have something that looks like this. And then take 4 carbon atoms and build butane. So build butane and build just an alkene piece. Then you're going to need 2 extra carbon pieces for what we want to do today. What's that? You having trouble getting your parts together?
It's so early in the morning.
It's so no. Look what we've got. Pieces go on the inside. Right. Pop.
Oh, you go through them that way.
There you go.
This way.
Should look like this. It will have 120-degree bond angles approximately. If it doesn't look that way, you don't have it. Now I'm going to take 2 extra carbons, and I'm going to put on this alkene to where one of the carbons is on each carbon of the alkene. So how many total carbons do I have in this molecule? I've got 4 carbons. And how many carbons do I have in this molecule? Also 4 carbons, right? So this is a butene, E-N-E for an alkene. This is butane for an alkane. Okay? They only differ by 2 hydrogens. This one is saturated. This one is unsaturated. This one's missing 2 hydrogens compared to this one, right? And this has consequences. So if I look at my butane, I will notice that I can freely rotate around all the bonds. Why can I freely rotate? Because I have no pi bonds. Everything's sigma, right? And sigma bonds are cylindrically symmetrical. So I can rotate around that bond fairly freely. And you can feel that in your model kit, right? It's pretty easy to do. Now, if you take your alkene and you take those same 2 middle carbons, can I rotate freely around them? Not at all. You'll notice the model kit's actually pushing back on you, right? Yes, I know you can take your model kit and you can do that. But look what you did to your bond, right? That's not chemically relevant. This is another place where your model kit fools you, right? I cannot freely rotate around that carbon-carbon double bond, okay? And as a result, this has consequences. So for example, if I take this model, and I'm going to borrow yours for a second, and I'm going to switch it around just a little bit. Are these the same molecule?
Not the same molecule, but the same.
They're both butenes, but they are very different. These 2 methyl groups, as we would call them in this particular case, are on the same side of the plane, if we look at this as being a plane. Here, the 2 methyl groups are on opposite sides. We call this trans, and we call this cis. And from your reading, how can you remember cis? Cis is on the same side, right? I know that sounds corny, but it works. Cis is on the same side, right? Trans is the opposite, okay? These two molecules actually have different boiling points, different melting points. They give different spectra. Actually, if you look in that fingerprint region of the IR, you'll see differences. So they are very different molecules. Just taking two hydrogens from this, you go from free rotation to restricted rotation to something that we call geometric isomers, trans versus cis. Do I have trans and cis in this molecule? Not really, right? Because I have free rotation. I can rotate around these bonds. So does that mean if I could look with a magic microscope that all the time this is just freely rotating all the time? Or are there preferred conformations? Is this better or is that better? Pardon? Say it. There are preferred. That's exactly right. Right? And so we're going to talk about that in terms of these models. Okay? So, if I look at this model of butane and I hold on to one methyl group and the other methyl group, I'll notice that as I rotate, the methyl groups get closer together or farther apart, right? These are called different conformations. This is a different conformation than this one. Do they have the same energy? Are they the same stability? No. They actually have different stabilities, right? And so if I take these two methyl groups to be kind of large, are they going to want to be close together or farther apart? They're going to want to be farther apart, just like people, right? People don't like to be crammed into a room together, a tight room. They like to be kind of a little farther apart, right? Usually, all right? So we can't let the analogy get too crazy there. But these things have different energies. And analyzing the energies of these different conformations is called conformational analysis. And there was actually a Nobel Prize awarded to Sir Derek Barton for his work on conformational analysis, being able to play with model kits. He did a lot more than that. I mean, he was a very famous organic chemist. And worked right up until he passed away several years ago. Did an awful lot for the field. But one of the things that he won a Nobel Prize for was for his contributions to conformational analysis, okay? And so this fact that we can have these sigma bonds allows us to have different conformers. And it turns out you all are going to have to know something about conformers when you get into your medical school studies, because proteins and biomolecules can take on different conformers and fit in different spaces and interact with different enzymes, interact with different receptors, which gives rise to different effects. And so conformational analysis, while you might find it boring right now, turns out to actually be very powerful. Okay? Not to mention what we can think of if, for those of you who are in the materials science side of things, polymer science. Conformations lead to different structures, lead to different functions and different forms. Okay? So it's very important to understand something about these conformational analysis. Now, how do we represent a conformer? We're going to use what's known as a Newman projection. A Newman projection, okay? Now, here's our butane, and I want to know what the conformers are looking down the carbon-2, carbon-3 bond. I'm looking down this bond, and I'm going to see how that's projected onto a two-dimensional surface, okay? So if you look at it, and it's hard for me to hold it, okay? That is a Newman projection. This is a Newman projection. Yeah, you can build a model. You can actually build a little better model than these are. You can go outside when the sun is right above you, and you can hold your model kit, and it will give you the Newman projection on the sidewalk. Okay? They really are a projection of a three-dimensional object onto a two-dimensional surface. That's what a projection is. And we have to have a way of representing how we're looking at it. So I'm looking at this particular carbon. That's going to be the carbon that's in front, right? This carbon is behind me. It's the carbon in back. And the way that we represent that on a two-dimensional surface is with a dot and a circle. The circle represents the carbon that's away from me. It's the one in the back. The dot is the carbon that's right in front of me, right? So what's attached to this dot? Well, there's the bond that goes to the other carbon in the back, but we don't see that because we're looking right down that bond, right? You don't have to draw that. But what else is attached to this carbon? I got 2 hydrogens and another carbon, a methyl group, right? So we're going to have that Newman projection. Let's do this on the one that we've built. So there's the back carbon, there's the front carbon. So how do I draw the 2 hydrogens and the methyl group? How do I draw those? There's the front carbon. From the dot. Hydrogen, hydrogen, CH3. Okay? Notice it goes through the circle. That does not mean that it's also bound to the back carbon, right? How do I draw what's attached to the back carbon? That's what I have there, right? Now, if you had it like that, you would draw it a little differently, right? The front carbon would look like nothing changed, but the back carbon would have the position of these 3 groups in different positions relative, okay? So that's a Newman projection, okay? Very important to remember. The bonds to the front carbon are going to go through the circle and stop at the dot. One of the big things that students do, I don't know why you do it, I'm still trying to figure it out, but many of you will have the dot and the circle and everything bound to the back carbon, or everything bound to the front carbon. Remember, we can only have 4 bonds to carbon, okay? I think what happens is people start doing things quickly and not paying attention to where they're drawing, and they just sloppily throw things up on the page. It matters. Okay? If you have more than 4 bonds to a carbon, that's when my red pen starts to come out in full force. Okay? That's the one thing that you need to remember the most. Right? Carbon can have no more than 4 bonds in these types of structures. Okay? So, we're going to look at the conformational analysis of butane. Now, technically, for those of you who've had a number of your math classes, you know that we can rotate that in an infinite number of ways, right? But we're not interested in infinity here. We're interested in certain angles. And typically, organic chemists are interested in like 60-degree rotations, okay? It gives us an idea of what we're after. So, what we have, if you look at the back carbon, we have the methyl group up and the 2 hydrogens off to the side. The front carbon, we have the 2 hydrogens up here and the methyl coming down. That is that Newman projection. Everybody see that? Okay. It is called staggered and anti. It is called staggered because if I look down that bond, all of the atoms are staggered with respect to one another. I can see all of them. It is anti because the 2 largest groups, the 2 methyls, are 180 degrees to one another. Now, we're going to rotate 60 degrees. Which carbon did they rotate, the front or the back? The back carbon. Does it really matter which one we rotate? No, but this is the one that they start with. And so we rotate that 60 degrees. Now it's called eclipsed. Why do we call it eclipsed? Because when I look down that bond, I see this hydrogen is obscuring that methyl group. Like the moon eclipsed the sun a few weeks ago, right? Got in its way. That's what's happening here. All of the bonds are eclipsed. And my model kit's getting old and a little. But you can see, if I hold it just right, see how you can't see the hydrogen versus the methyl anymore? It just looks like one thing? That's because it's eclipsed. Okay? So we just rotated 60 degrees. We can rotate another 60 degrees, and we end up with what's another staggered conformation, because all the bonds are staggered. It's called gauche. It's when these 2 groups are getting close to one another. We can rotate another 60 degrees, and now we can have the 2 methyl groups that are eclipsing one another. I call this the methyl-methyl eclipsed conformation. We can rotate another 60 degrees, and we can have another gauche. Another 60 degrees, we have now another eclipsed. And then we rotate another 60 degrees and we're back where we started. Which one of those do you think are lower in energy and which ones do you think are higher in energy? Okay, so the methyl groups are getting close. That'll be higher in energy certainly than the anti, right? What about the hydrogen versus the methyl eclipse? Is that going to be higher in energy or lower in energy than that? It's going to be a little bit higher. That's going to be a little bit lower. That's going to be really high. And then it's going to start repeating, going down, right? And so you all will remember that I have some software that allows us to actually determine. I have built a model. Let me turn this down just a little bit. Maybe that'll help, just where you can see it a little bit better. Is that better? And what you can see is I've built in the computer a model of butane where the two methyls are actually eclipsed to one another. And I've told the computer to go through and rotate it every so many degrees. I can't remember how many degrees I actually told it to rotate it, and calculate the energy for that particular conformer. And so what you have here is a plot of the relative energy of those conformers versus what's called the dihedral angle. Okay? So this is a dihedral angle of 180 degrees. This is a dihedral angle of 0. The computer likes to start at 0, so that's why we have 0 right there. Notice it's way high in energy. It's the highest energy point. So what happens as we start to rotate around that carbon-carbon single bond? Notice the energy starts to go down as the two big groups start to get away from one another, right? And this lowest little local minimum here is which conformation? It is a staggered, but it's a special one. Staggered, that's right. Notice it is not the lowest energy, but it is relatively low, right? It's what we call a local minimum, not a global minimum. Now, as I start to rotate again, why is the energy going back up? What's eclipsing? The hydrogen on the back carbon and the methyl on the front, as I'm holding it right now, right? Which I think I'm holding it just as you have it on the screen. And notice at this very top of the mountain, this little hill, it's where we have the hydrogen methyl eclipsed. Now what's going to happen as I start to rotate past that? It's going to decrease again until we reach the global minimum at 180 degrees, which is the what conformation? That's the staggered. And so we have the big group and the big group far away from one another. Anytime you're doing conformational analysis, you need to identify the bond you want to look at. I have to tell you that. I'd have to tell you, look down the carbon-2, carbon-3 bond of butane. Because you can also look down the carbon-1, carbon-2 bond and do the same type of analysis. It's just not very exciting here. So you look down the carbon-2, carbon-3 bond. Once you've identified that bond, find the big groups. Those big groups are always going to want to be as far apart as possible in the lowest conformation. Okay? So you have to, this is where models come in handy. If you had a methyl group and an ethyl group, ethyl would be much larger than methyl, right? And you can see that because you built the model. Okay? So that's why model building becomes pretty important. And so I can actually play this, and you can see that the energies change. It mirrors on both sides. It's just symmetrical, right? And so the energy happens. So why is it that we have you buy this model kit? Because can you really tell the energy difference from that versus that just by rotating? I mean, it doesn't feel much different, right? I don't really feel the effects of these two methyl groups getting close to one another, right? But the computer can tell that, right? So why don't we have you buy the computer program instead of these models? Because these are 40 bucks. Computer program is 2,000. Okay? So I'll build the model in the computer and show you that, okay? And you want to know that the big groups want to be far apart from one another. And so I like to hold them in my hand, and you can actually, when you get close, you can actually feel your hands coming together, right? So you know that that's got to be a high energy conformation, okay? Let's pause that. All right, we got a little bit of time. Name that, build a model, and then look at the conformations down the C2, C3 bond. What's the name? 3-methyl what? Pentane. And we want to look down this bond, right? So if my eyeball's out here, I want to look down that bond for the conformations. Your model should look something like that. All right. And we want to look down which bond? We'll look down C2, C3. So as I have it, the carbon that's facing you is going to be the front carbon, which it has the 2 hydrogens in the methyl group. And if I look at the back carbon, that's going to be what? The dot or the circle? The circle, right? The back carbon is the circle, the front carbon is the dot. What's attached to the back carbon? I've got a methyl group. What else? An ethyl group and a hydrogen. So on the front carbon, I've got 2 hydrogens and a methyl. Which of those 3 is the large group? The methyl. On the back carbon, I've got an ethyl, a methyl, and a hydrogen. Which one of those is the large group? Ethyl. So I've got ethyl large and I've got methyl large, and they're going to want to be 180 degrees to one another in the most stable conformation. Okay? So I've got those 180 degrees from one another, so that means that the front methyl group and the back methyl group are going to be in what relationship to one another in the most stable conformation? They're staggered, right? But they're also gauche, right? So I've got the 2 big groups as far apart as possible. They're always going to want to be as far apart as possible, okay? Yes, that puts the 2 methyl groups far apart, but now we're putting a large group and another large group closer to one another. Notice how close they're getting. That's bad, okay? You always want those large groups to be as far apart as possible. This takes practice. I've been doing this for over 20 years. I still build models. I don't build models anymore with this little plastic kit. I use my computer to do it. But I build models because it can get real complicated really quickly. Now I've got your inverted lecture 3 that I'm going to hand back today. I've decided tonight at 6 o'clock I'm going to do a little workshop on the inverted lecture. Bring it with you. It's voluntary. Come if you can. 6 o'clock in the tutorial center. Yes, I can do that. I can do some type of screencast or something like that. Okay, so we need to practice with our arrows. That was the big thing that I kept seeing some minor errors on. But by and large, I'm a lot more happy with your performance on this inverted lecture. You're starting to get the idea of how to answer questions properly. I like that. So I'm going to call out your name. Please raise your hand, and I'll give you your assignment.